welcome to the Westin MCAT podcast with your host, Ahmed
and Eric Olson.
Welcome back, everyone, to another episode of the Westin MCAT podcast with Ahmed and Eric. Today, we're going to talk about stereochemistry and some of the different classification systems and how they sort of manifest as testable topics on the MCAT. And so, before we get into that, first of all, hopefully everybody had a great Thanksgiving with family. By the time this episode gets aired, it'll have been a little bit over a week since Thanksgiving, but notwithstanding, hopefully everybody got to enjoy some time off. Eric, you do anything fun over the break?
Had some friends come visit.
Nice.
Some college friends. They came and stayed with us, and it was fun. I cooked a turkey, which I haven't done before. I guess I'm a dad, so feels like kind of a thing you're supposed to do.
Right.
And it was a lot of work. Not just the turkey, but the whole meal. Chloe and I had always been to someone's, her parents' house or my parents' house for Thanksgiving in the past, and it just didn't work out, and we're a little bit further away this year. So it was kind of a new experience, and I came away from it I don't know if I feel an obligation to continue the tradition just because it's what you do for Thanksgiving, but it was a lot more work than I thought it would be. And then, you eat in 15 minutes, and then wow, I just spent 2 days preparing for this,
Yeah.
It is what it is.
I'm sure the friends enjoyed it though.
Yeah. They had a lot of good things to say, but at the same time, I don't disbelieve them, but also, if I went to someone's house and they had spent 2 days preparing a meal, then I would also be like, this was great. This is the best meal I've ever had,
Yeah. There's a little bit of friend, bias and favoritism there, but I'm sure your cooking debut was exceptional.
I do actually have an interesting thing that I wanted to share, which is that we're doing residency interviews this week, and
okay.
And I'm on the interview committee of sorts. There are, for dermatology, just for a little bit of context, you do an intern year that's separate from in most cases, is separate from your categorical dermatology program. And so, we'll do interviews this year. I'm a PGY2. I'm a first-year dermatology resident out of 3 years of dermatology. The people that we match this year are not going to be here next year. They're not going to be here till the following year.
Right.
So I will be a third year. I'll be my last year, and the people we're matching right now will be first year dermatology residents. So the PGY2s, the first year dermatology residents, have a special interest in who's matching, because we're the only ones out of who's here right now who will still be here in 2 years when the new residents get. Does that make sense? So they have two of us that are on the match list committee, so to speak. And so myself and one other resident we're going to do some of these interviews, and it's interesting as I've been thinking about, I think about it in context of med school interviews and things that we talk about on the show. But it's interesting, I might have to talk to Jaden, because I don't know what his interview experience was like when he was interviewing at Harvard, but the interviews that I did at Michigan when I was a med student for prospective students were all short form. And so some of those were we would have, a question that we would ask and kind of hear what people had to say. And a lot of times they were different sorts of things, scenarios where we would pose something, or sometimes we would do a role play sort of thing. And it really just depended on the week or the month that you were doing interviews. And this is a much more kind of long form, you're in a room, a Zoom room, but you're in a room with someone for, 10 or 15 or 20 minutes, and you just kind of have a conversation. And I think we have some prepared questions that are given to us.
Yep.
But it's just different, thinking about how to evaluate individuals. And I guess I would relate to people. And again, I think it varies based on the institution and may vary from med school to residency as well. But from what I can tell, the interview is kind of its own thing. separate from the rest of your application. And so when we go back and kind of decide who we want to be at the top of our rank list, I think the interview comes into play as well as all of these other things in the application. But I'm not going into the interview like having read everything that they,
Right.
coming in with this bias of like, oh, this person went to this school and is really smart. You know what I mean?
Right.
So it's kind of interesting. Like, I think it hammers home to me a little bit of I guess, the importance of the interview and your ability to, make an impression based on your conversation, your interaction with your interviewer, aside from everything else that has been shown about you on paper.
Yeah.
Right.
No, I think, like, it doesn't matter what stage you're in life. I think like your ability to communicate with people, to make an impression, to answer questions, right? Like you can be the best conversationalist, but if you don't answer the interview question, like, you're not going to score very well.
You're not doing it right. Yeah.
Um, so, and like it translates to being a doctor too, right? Like a patient comes in with pain, you got to balance, listening to their story, but also, starting to put a plan in place to address the pain, right? Like there's always an
Mm.
outcome or an objective, but there's a process to getting to it as well. And that's kind of how I've always viewed responses to interview questions. Like there's an outcome that I need to reach, and there's a process that I want to go through to get there. And if I do those two things right, I'll feel sort of pretty happy with
Yeah.
the response. But
I
no,
like
it's
that. I like
interesting.
that way of thinking through it. There's an outcome that you want, but you have to kind of get there. You can't just jump straight to it.
Exactly. Yeah, it was good advice that I got from a friend of mine before I went into the interview process, and it's just kind of stuck with me since. But no, it's cool that you're getting to pick or getting to contribute to picking the next generation of dermatology residents there.
Yeah, it feels like a lot. It feels like a lot of responsibility, And it's funny because you're right. I'm not sitting down and making the list myself. I think there's a lot of
Right.
discussion that goes into it, but it does feel like it feels like a lot of weight, which is funny because, my day-to-day is like taking care of patients, which is its own kind of weight, but
Yeah,
this hits
man.
close to home, because I've been through it, and so how much stress is a part of all of that. And
Right, right. Wait, all I'm going to say is just remember the names of the people that you scored favorably, and if and when you see them in a couple years, maybe you get a coffee or a lunch out of it. Who
there
knows?
you go. There you go. Maybe so.
But in any case, maybe something less or more exciting, depending on where you're coming from. But stereochemistry was always, a topic for me on that's a horrible transition.
No, I
Wow.
liked it. It was a good try.
It was a terrible try, but that's completely fine. Yeah, we were literally just talking about objective and process. Process was out the window. But in any case, stereochemistry is a weird sort of topic for a lot of people because unless you have like a model kit in your hand, it's kind of hard to just like work through like manipulating molecules in space. And like literally, as I said, model kit, I could hear like the clicking of like the oxygens and whatever just coming in and out of place. But
Bonds. Yeah.
um, I think it'll be helpful for us to start with like, okay, how is stereochemistry tested on the MCAT? Like, what are the contexts? I think from a big picture standpoint, you want to know the R and S as well as the sort of cis and trans
Hmm.
classifications. Where do they apply? R and S definitely to the amino acids. You want to know which ones are R, which ones are S, which ones are achiral. But I've seen a lot of questions too where um, you'll get just a structure in the question and be asked about either the uh the stereochemistry just sort of directly or indirectly through like an SN1 or SN2 mechanism where you've got a change in stereochemistry or you've got um, a, a racemic mixture, as we call it. But that's kind of like from an overview standpoint, what comes to mind. I'm curious, Eric, if there's anything you want to add to that in terms of what's
No,
testable.
I think you're hitting on the high points. I feel like where I mostly saw it as in this context that, you're talking about of like enantiomers and this R
Hmm.
versus S and like rotating polarized light and stuff like that. I think those things can come up. I certainly don't think it's impossible to have a question where they just give you a molecule and ask you. But I've seen questions before where they have some sort of reaction as, maybe a reaction as part of the passage where they have multiple steps and multiple species within those steps.
Right.
And they'll pick one out and say, maybe they have a figure later on that's telling you about which way the R versus S is rotating light and things like
Yep.
that. And then they may say, look at this specimen and tell us, what do you think about its ability to rotate light, or which way is it going to rotate light and things like that. And so
Right.
maybe putting a few different steps together based on what they're giving you in a passage. But to me, I think, and something we'll touch on, but like some of those properties of enantiomers, like what are they exactly? How do you determine if there are or S? And then kind of what are the interesting kind of factoids about those that we're talking about here of rotating light and things like that, and
Right.
reacting differently with, other enantiomers, things like that, I think can be testable as well.
And let's maybe start there is just like defining some of these things, right? So starting with, big picture, what is an isomer? Right? An isomer is, or isomers are two molecules that have the same molecular formula, right? So they have the same numbers of atoms, but somehow those atoms are put together differently.
Mm-hmm.
They could have different bonds, in which case we would call them constitutional, or they could have different arrangements in space, in which case we would call them stereoisomers. The constitutional ones don't really come up on the MCAT. Like if it's a different bond, it's an isomer, but there's nothing in the form of R or S configurations, because you can tell them apart just from the bonding arrangement, right? Whereas the R and S helps us tell apart isomers that have the same bonding arrangement, essentially, or the same
Now,
connectivity.
when you talk about constitutional isomers, tell me a little bit more about like what exactly you mean about being connected differently. Like what
Right.
I'm thinking about is like if you, without using like the IUPAC naming formulas and stuff like that, but if you had, like an octane that ended
Uh-huh.
up having an alcohol group on it on the very end,
Yep.
that's a constitutional isomer from an octane that would have an alcohol group like in the middle of that,
Correct.
right? So I
Yeah.
guess I learned that as structural isomers is
That's
the,
it.
the term that I learned. So I'm just making sure we're on the same page.
Yeah, yeah. No, they're synonymous actually.
Okay. Okay.
Constitutional and structural. I've always gone with constitutional because in my head I think they're constituted differently.
Sure.
Or they're structured differently, I
Structured
guess would probably
differently.
be
Yeah, I mean,
easier. But
whatever. But
yeah,
I agree with you in that, I don't think this is gonna come up nearly as much.
right.
It's like you said, it's helpful to know maybe that it's the same number of each particular type of atom, right?
Yes. Yeah.
But aside from that, like I don't even know if this term really will come up. I think it's testable in a strictly like, is it a possibility sense? But I don't know if I
Right.
anything testing this specifically.
I agree. What really what really does matter though are those stereoisomers.
Yeah.
Um, Starting with maybe cis and trans, those are referring more to double bonds,
Hmm.
right? So you've got a double bond and you've got, two different groups on one side, two different groups on the other. Cis basically means the higher priority groups are on the same side of the double bond, either above it or below it.
Yeah.
And on that note, priority, yeah, we assign priority based on atomic number. So the bigger the atom, the higher priority it has. Quite literally, the more weight it holds. And so we use that that label way back when it was implemented was probably arbitrary. But it's just a way that, scientists can communicate with one another, specifically which structure you're dealing with in an objective sense. But so yeah, cis meaning same, trans meaning opposite. That's also the EZ sort of labeling. I remember Z for ZAME. So cis would be the Z, and then trans would be the E.
Z
Uh,
for Ziz. is what I
Yeah,
see
that
that thing.
works too.
I like this. We have different like mnemonics, but they're also kind of the same.
Yeah, and I mean,
I would add that with cis and trans, the cis isomer is going to be slightly, again, like these are kind of details, but as long as we're talking about it, the cis isomer is going to be slightly less stable,
yes,
because you have like the larger groups, generally speaking, are going to be, if your backbone is down here, your larger groups are both going to be up here, and so there's like some
right.
steric hindrance going on here. Whereas in a trans group, you have your backbone here, and one group is off to this side, and one group is over here, and so there's more distance between those big electron clouds,
Yep.
which makes it slightly more stable. And again, is that testable? Technically, yes, but probably not. And the other thing I would add, I think for all intents and purposes, thinking of the priority of the groups by atomic number is certainly appropriate. Um, my only caveat is like I have actually seen a question where it was asking about um, isotopes of hydrogen. And so
Okay.
what is it when there are two neutrons and a hydrogen?
Um, two neutrons would be a tritium, one would be a deuterium.
Yes, and so you would have like a hydrogen on one, or like a deuterium here and a deuterium here. And so
Yeah,
like the atomic number is the same between, hydrogen or deuterium or tritium, but the mass is different, right? So like
right.
strictly speaking, if one is heavier and has a greater mass than the other, then that would take priority. But again,
Yeah.
I think pretty unlikely to come up in reality.
Yeah, and I mean, like you said it best there, Eric. The simplest answer is just always go by atomic mass. The bigger the atomic mass, the higher the priority. And so with those cis trans isomers, that's really what it comes down to. If they're on the same side, it's cis with a Z. If they're on opposite sides, they're trans represented with the E.
Mhm.
The other big sort of domain, we'll call it, of stereoisomers are the R and S configurations. And so these are around chiral centers as opposed to, those stereogenic centers. And maybe just to distinguish between the two, a stereogenic center is any center at which isomers exist.
Mhm.
Chiral centers are a specific type of stereogenic center where it's only single bonds with four different groups. And so when we have these chiral centers, we can label the sort of what we call the absolute configuration, meaning it doesn't change no matter how you look at it, of that chiral center. And so to do so, it's a bit of it's an art almost. It's this
Yeah.
mental gymnastics, and
Mhm.
there are shortcuts to do with pen and paper, but it can easily be one of the most frustrating things to learn, not because it's impossible, but because it's so difficult to visualize and it's also so minimally tested on the MCAT, sometimes if at all. I think like you take enough exams, you're guaranteed to get a stereochemistry question, but
Yeah.
any single exam in isolation, it's probably like 50-50 whether you see one or not. Um, but in any case,
But if you
uh,
know it, then it's an easy question, right?
true. And that's,
Kind of one of those things.
I mean, yeah, it's how you have to look at it, right? Like if you can figure it out, you've just added to I don't want to say you've added to your score, but you've made your life easier come test day, right?
Yeah.
You get
Yep.
rewarded for putting in that work. Um, but so to start with this RS classification, we need to start by getting the lowest priority group pointing into the plane with a dash. Almost always that's going to be a hydrogen.
So the dashes in like the notation on just so we're all on the same page, when you are writing, a chiral center has four different constituents or four different species to which it's bonded, right?
Yep.
And so you in your like spatial depiction of a
Mm-hmm.
chiral center on paper, often they're depicted with two, normal weight lines that
Yes.
in bonds, and then one is dashed and
Yep.
one is bolded or, wedged, I guess,
Yep.
depending on how you look at it. And so the wedged bond is coming out of the page at the reader, correct? And then
Right.
the dashed bond is kind of going back into the page. And I think you have to like, did you ever think, I'm sorry to interrupt you, but did you
No,
ever
I wasn't
think
saying
about
anything.
did you ever think about doing dental school?
It's funny. My mom was like advocating for me to
Yeah,
consider it, but not even in the slightest. Now
neither
this
neither did
disgusts
I.
me.
Neither did I. Yeah, I'm not a fan. And funny enough, there's some mouth stuff in dermatology, so now I'm doing it anyway. But
Yeah.
I never thought about dental school, but at one point I must have had a friend who was getting ready for the DAT, which is, like the, at least in the United States, is like the dental admissions test. I don't know if that's
Yeah,
actually
yeah.
in sport, something like that. And I looked at like some of the different sections, and there's a whole section on there, or at least there was, about like spatial reasoning. Have you ever seen this?
Yes. Yeah, yeah,
Where
yeah.
they'll like draw like a 3D image of like some blocks in some configuration, and then they'll be like, which of these four answer choices is the same structure? And then they have
Right.
like all turned around, A, B, C, and D, and you have to
Yep.
like, it reminds me of this sort of thing,
It
because you have to like build the structure in your head, and then you have to kind of like turn it around and look at it from the other way and figure out what it is. You know what I mean? And so sometimes I think of that when I'm thinking about when I'm thinking about the enantiomers and R versus S and all of that. And I think, that's the way that you certainly like it helps to draw on a piece of paper, but I also
right.
think you have to be thinking about what this actually looks like in space. And part of that is recognizing like, because you have a chiral center, generally speaking, a carbon, which is bonded to four different constituents. Those angles are not going to be at 90 degrees, right? We know that that angle is
Right.
109.5, I think is what it is. And so you
Right.
have to think about like, what are those bonds going to look like? It's not going to be one straight up and one straight forward, because that's a 90-degree angle. And so instead you have all of these constituents that are competing for space. And in so doing, they all spread out as far away from each other as they can. And the only reason I bring this up is because I think until you see, and I would, if you are not following, like I would just look up on Google Images, like, you know, 109.5-degree chemical bond. And I'm sure with that you would find a picture of this idea of like something that's bonded to four different constituents. Because that's kind of what you should be thinking about how this looks in your head. And then you stick one of those constituents, the one with the lowest molecular weight, with the least priority, which is what
Yep.
I was getting to, you stick it into the back of the page. And so you take it like it's sitting in front of you, and you're kind of building it in front of you, and you stick that one into the back of the page, and then you draw your other three. And at that point, you kind of determine the priority of those other three constituents, and you figure out if you're going to go clockwise or counterclockwise in, is it ascending or descending order of priority at that point?
Descending order. So starting at the highest priority, working
Do you start at the
down.
highest and you work your way from one priority number one to priority two to priority
Right.
three? And if it's, if that makes a clockwise rotation, then that's your R enantiomer.
Yeah.
And it makes a counterclockwise rotation, then it's an S enantiomer. And so it has to do a little bit with, your mental configuration of these. But at the end of the day, if you can figure out, that dashed means into the page, that wedged or bolded means out of the page, and then you just determine the priority of each of your constituents based on atomic mass, like we talked about, um, then you can stick that lowest priority into the back of the page, and kind of go from there and figure out from high to low what the rest of those priorities are, and figure out if you're going to have an R or an S. And
Right.
like Ahmed said, like, is this going to come up? Not necessarily. I think your ability to do this particular action of determining an enantiomer, if it's R or S, is not necessarily going to come up. I think having a working knowledge of what this means, and like this idea of mirror image molecules, is helpful. I think having that understanding will be helpful. Needing to go through this process is a maybe. I don't know, would you agree with that?
Yeah, I think obviously it's going to be pretty question specific, but I think to your point, Eric, like will there be a time where you need to go through like a full, stereochemical classification on multiple molecules? Possibly, but unlikely. Oftentimes, it's more so in the context of, you're given a molecule, you might be told it undergoes an SN1 or an SN2. What product or products would you have? Right. So just simply looking for, a racemic mixture or an inversion, respectively. I think the biggest thing with these classification systems, though, is just getting comfortable labeling them, right? Like get comfortable getting a molecule, orienting it correctly and drawing your circle, or leaving it oriented incorrectly and taking the opposite if
Yeah,
that's appropriate.
perfect. I like that too. Hmm.
Um, there's a lot of like techniques with stereochemical labeling. And it's not as easy as just, leave it wrong and, um, take the opposite, because sometimes that doesn't actually work. But, there's this idea of like switching two pairs of groups, for example. If you flip the positions of two different pairs, you end up with the same molecule. Um, and so, that's just one small example of something you can do to make your life a little bit easier.
Yeah.
um, the stereochemistry was something that I struggled with. Like I struggled with it in my undergrad. I was introduced to it briefly in like AP Chem in high school, and I never understood it.
Hmm.
And I didn't necessarily love it on the MCAT either, but it's something that you get enough you get enough practice at something with feedback, and eventually it starts to piece itself
Yeah.
together. I think stereochemistry honestly is one of those things, but it's maybe a little frustrating in the sense that it doesn't have any obvious visual, um, methods to learning, or just methods to like appreciating it. Like, for example, like, with physics, for example, at least you can see how, okay, yeah, I could see that in the real world, right? Or with some of the lab techniques, okay, I could see that on a gel. Stereochemistry, like, it's not as intuitive, which, like I said, I think contributes to maybe some of the frustration, but it is something that can be governed by objective rules. And I think that's what I would always fall back on, is just knowing like, okay, there are rules that I can follow to get to these outcomes. I just got to get
Yeah.
more practice doing it.
Yeah. There are a couple of other things that I think, from a perspective of like, this is really hard to learn, are maybe a little bit easier to learn because they're not so like structurally oriented as far as like you having to understand how something's oriented in space. For one, this idea of like dextrorotary versus levorotary, and I think we mentioned briefly that enantiomers, and I think, we haven't really talked about this, but the idea behind enantiomers being that they are like essentially the same structure, but mirror images of each other. Right. And I think the traditional example is like two hands. So like, your hands look exactly the same,
Yeah.
but if you try to overlay them, like they don't overlay perfectly because they are mirror images of each other, right?
Right.
Um, so one of the properties that often will come up with enantiomers is that they have the ability to rotate polarized light. And frankly, like when I took the MCAT, I didn't really understand what that meant, but I knew that it was a thing. And I think that's honestly helpful enough. Like you don't have to know how it works or like what polarized light really is. You just need to know that they'll rotate it. And so, there's not a hard and fast rule necessarily for like which, does R and enantiomers always rotate in one direction and S always rotates in another direction. That's not the case. Like each enantiomer is different. But when you take an enantiomer and you shine a polarized light through it, then whatever rotates it clockwise is termed dextrorotary. Whatever
Right.
rotates it counterclockwise is termed levorotary. And then if you have a mixture of those two, which is what Ahmed is talking about when he's saying a racemic mixture, which is equal amounts of, or actually I don't know if racemic is necessarily equal amounts, is it, of each enantiomer. I don't know.
Yeah.
But in any case, if you put a polarized light through a mixture of both enantiomers, then it won't rotate.
Right. It's
Um,
almost like, if you have like a charge moving through, like a charged particle moving through an electric, uh, moving through moving through air, let's say, and you have negative charges on both sides of the path that it's going
mhm,
down, like
mhm.
it's not going to end up moving anyway because
Right.
this negative charge will move it one way, this one will cancel that out, and
They
it'll end
cancel
up
each
just
other
going
out.
straight through, right? Same
Exactly.
thing with the racemic mixture. One wants to rotate this way, the other rotates exactly the opposite way, and they cancel each other
Yeah.
out, right?
I think the caveat would be, if you had a mixture that was like 90% R
Right.
enantiomer, 10% S, then you have a lot more R, so it will rotate in one direction, just not as much as if it
Right.
were a pure product. Uh,
Right.
because they are like mirror images of each other and they have a lot of the same properties. So like if you have an enantiomer R, a collection of R versus S, and you look at the boiling point, it's going to be the same, right?
Yeah.
Like those sorts of things, the physical properties are going to be the same. Where you're going to have some differences. One, we talked about polarizing light, and the other kind of big difference that we see is that they will react differently with other enantiomers. And, again, like you're not definitely going to get a question about this, but the way that I think about this is like with a handshake, right? Or like picking up a piece of wood. Like if you had
Hmm.
a pole, like a uniform pole that's, or like a ruler, for example, and you pick it up with your right hand, you're going to have a couple inches sticking out on either side. If you pick it up with your left hand, it's going to look pretty much the same.
Right.
But if I try to shake your hand, Ahmed, if I give you my right hand and you give me your right hand, it's gonna, they're gonna come together and it's gonna be great. We're gonna have an awesome handshake.
Yeah.
But if I give you my right and you give me your left, because those are both kind of chiral substances, so to speak, and
Right.
they're not gonna work out the same, right? And so you have a different reaction pattern with
Right.
two different enantiomers than you might have with, an R and S enantiomer versus something that's not chiral. It's all going to react the same.
Right.
So just some things to be aware of. Again, these are kind of more factoids, and I wouldn't expect them to like really get into giving you something where you're going to be reacting to chiral centers. Like we're not at a point where we would be expected to, generate a product from something like that and really understand the nuances of what those differences look like. But I think being aware of those sorts of properties can be helpful on some questions.
Yeah, and I think you made a great point there about some of the properties comparisons, right? We said that reactions are stereochemically specific, right? So enzymes work with only one of the stereoisomers, right? So
Yeah,
enzymes can be a really great way to separate different enantiomers or diastereomers because the rotational plane polarized light identifies that there's isomers present, but it doesn't actually separate them.
hmm,
But you made another point as well in that they have the same physical properties in melting point, boiling point, index of refraction, solubilities, all that density. Where interestingly enough, they differ is in smell. And that's
Oh,
something
really?
that I find, and if you think about it, it makes sense, right? Because the
Yeah,
receptors in our nose are stereo specific.
sure. Or
And so a
protein.
different stereoisomer may trigger, the olfactory neurons from a different receptor, and we perceive that as a different smell. And I remember I was going through a passage with some students the other day, and the passage in question we had one isomer smelled like mint and another smelled like rye bread. And it's so interesting that just the orientation in space causes it
Yeah.
to interact differently with our nose. That manifests as two wildly different smells.
I wonder if that's a real, do you think that's a real, like, enantiomer pair that rye and mint are like
Let's find
enantiomers of
out.
each other? I was gonna say, I wonder, that would be like a good organic chemistry lab experiment, but I don't know how you would separate the enantiomers. I think that's like really advanced techniques from what I
Yeah.
would
And
know.
so that molecule I was talking about is called carvone. Um, Carvone has It's found in mint leaves. Or sorry, the levorotary form of carbone is found in mint leaves, and the
Uh, extra
dextrorotary
rotary.
form is found in caraway seeds, which is used to flavor rye bread and other
Right. Yeah.
some other foods. So
Cool.
wild, right? They have the same, same mirror structure, same boiling point, same density, same solubility, um, opposite rotations of plain polarized light, but just completely different smells.
Yeah.
And that's just one of the things that makes science so cool, in my opinion, is like you can have these things that are almost identical, but in like this one specific property, they're entirely different. Um, and it's cool how, the science works out that way. But in any case, to recap, right, we looked at our two sort of major classification systems, the EZ and the RS, right? We talked about how Z was for cis or the same, however you want to put it, where we've got our highest priority groups on the same side, trans being the opposite. We talked about the cis configuration being a little bit less stable in terms of priority, right? Based on atomic mass. And, you do that and everything else will work itself out. And then with the RS, R is going to be for our clockwise circles, S counterclockwise. And it really just takes a little bit of practice, making sure we've got that lowest priority group on the dash into the plane of the page. And then from there, we can apply our labels. Am I missing anything there?
No, I think you're catching everything we recapped. I would just add one other thing. I feel like I'm picking out like real kind of esoteric things that are not necessarily going to come up, but I think are helpful to know or at least be aware of. I have seen a question before that asks you how many isomers are possible. And I think there's a very simple formula that I think is worth knowing. And it really is based on this idea that you talked about, Ahmed, before about what a chiral center is. And it really simply is an atom that is bonded to four separate groups. And so usually we're talking about carbon because we're talking about organic structure.
Right.
Theoretically, it could be some other atom that's bonded to four other things. But, what is it? Silicon, I think, that is like the next same group or whatever. So sometimes you'll get a question where it would show you, a structure and say how many enantiomers are possible in this structure. And so what you need to do is to be able to identify where the chiral centers are. And so again, this takes some awareness of like looking at a chemical structure and determining, I think the place where they might get you is that you have to remember that there are hydrogen atoms that are coming off of these, when you have a diagram that's not giving you every specific atom. Those hydrogen atoms are often not notated and they're implied.
Right.
You have to recognize, that counts as a specific group.
Yeah.
And so in a given structure, you would go through and determine where all the chiral atoms are, where all the chiral centers are, and kind of count them up, right? And so looking at, which of these atoms have bonds to four separate and distinct groups. And when you do that, then you can do a formula to determine how many enantiomers are possible. And that formula is the number of possible enantiomers equals 2 to the nth power.
Yes.
And being the number of chiral centers. And so if you think about it, if there are no chiral centers, then the nth power would be to the 0th power, which is anything to the 0th power is 1, right? So you have one enantiomer possible with no chiral centers. If you have one chiral center, it's 2 to the 1st, which is 2. You have, an R and an S. If you have 2 chiral centers, it's 2 to the 2nd, which is 4. And so you could have one enantiomer being an R, the other being an R. You could have one being an S, the other being an R. You could have one being an R, the other being an S. You could have both of them being an S. And so those are 4 different variables or outcomes, I guess I would say. And so, I won't bore you by going any further, but, the idea is just that. Like, if you can figure out how many chiral centers there are, then you can very simply figure out how many enantiomers are possible. And again, that idea that any one of those centers could be one mirror image or the other mirror image. And any string of mirror images connected to each other based
Right,
on
right.
how many chiral centers there are.
100%. And I think I have seen a question on an MCAT, like
Yeah.
how many stereoisomers are possible in this molecule. And like you said, number of stereocenters, 2 to that exponent. Yeah, I think really we've touched on most, if not all, of the applications of this material on the MCAT. As per usual, though, now as a viewer or listener, right, try to take what we've talked about today and now apply it to practice questions or reflect on it, use it to make more sense out of your notes, etc. Right, and reinforce what we talked about today with some good practice. But once again, I hope everybody has had a great Thanksgiving and is getting excited for the holidays coming up. Keep working hard, right? Finish the calendar year strong. Think about all those New Year's resolutions you had way back when. See if there's any you want to catch up on. But keep up the great work, guys, and we'll see you on the next episode of the Jack Westin MCAT podcast. Take care, guys.